In this lecture, we're going to move to a new topic. We're done with homology. New topic, no more homology. And we're going to talk about something called smooth manifolds. Now, you probably already know what a manifold is. If not, that's not a problem. We'll define it. And then we're going to specifically be interested in what are known as smooth manifolds. And smooth basically means differentiable. It means a little bit more than that, but it basically means differentiable, which at first sounds a little bit confusing because this is topology. We talk about continuous functions. But there is a way in which you can bring calculus in. And essentially what the idea here is the idea is this, that the most important topological spaces that we care about, that we study in topology, are manifolds. And most manifolds are smooth. So we'll explain what that means. Not all manifolds are smooth, but those are extremely pathological ones. The ones that we generally come across in practice in topology are going to be smooth. And the whole purpose of doing this is by introducing calculus, or analysis if you prefer to say that, on a manifold, it makes many, you can say, arguments a lot simpler. Because you can then take advantage of the power of calculus, right? Calculus will then allow you to be able to say things that you otherwise cannot say. And we're going to talk about differentiation, we're going to talk about integration. That's going to come in, and then you will see how it has an interplay between topology. Now, maybe just to show you an example of what I mean, it makes many arguments simpler. So here's a question you had on the homework, and this was a fake proof that the two-dimensional sphere is simply connected. Okay, so the way the proof goes is you pick a loop, let's call it F in S2 at the point P. Okay, so here's like a picture. So here's S2. You have some point, let's say it's the North Pole without loss of generality, and we have a closed loop, and we want to show that you can shrink that loop down to a point. Well, what you're going to do is you're going to pick Q not on F. You're going to pick a point that's not on the loop. Technically, we mean on the image of the loop, if you want to be a little bit more specific. So you pick a point Q, and then what you do next is then you stereographically project from Q to map. So S2, take away that point onto R2. Right, so when you stereographically project from that point, you can then map this punctured sphere minus the point into R2. And this is a homeomorphism. And then so the point will get mapped somewhere, does not really matter where, and then you'll have a loop in R2. And then you would say that since R2 is simply connected, we can shrink the image of F in R2 down to a point. And that's basically the proof right there, that you can shrink this blue path down to a point, and then that homotopy can then be transferred over back to the sphere by using the homeomorphism, and then you could just shrink that down to a point, and that shows that the sphere is simply connected because all loops on the sphere can be shrunk down to a point. Well, the problem with this argument is you have these very strange paths, functions, when we talked about curves, that they're called space-filling curves. And it is conceivable that this is a very pathological loop that completely fills out the entire sphere. And then this argument breaks apart. So the way you can make this argument, so that there's a flaw in the argument. So the way you can fix this argument is you basically have to do this. You would have to argue that we're not going to do it because this is closer to analysis than to topology, but just to give you an idea of how you would do it is you first have to argue So you first argue that the homotopy class of F can be replaced by a different representative so that G is a loop at P, but G is smooth. So anytime you have a homotopy class, you can always replace it by a different representative, and we're arguing it is possible to replace the original function that may not be smooth, whatever that means. We're going to have to define that. But you can replace it by something that is smooth. But intuitively, you kind of know what it means. It just means the path has no sharp corners. And then you repeat the same argument by using G instead. Okay? And once you know that G is smooth, so first of all, you might ask, how do you know, like, how do you justify that? Well, the idea is it's sort of like a perturbation type of an argument. The idea is that if you have a function and it's highly irregular and it has a lot of like sharp corners, you can sort of draw something that sort of is very close to it, but it kind of goes, it makes the corners rounded or something. So it just, slightly perturb it so that the corners are rounded instead of sharp. And because these functions are very close to each other, it makes sense that you can get like arbitrary close and you make it smooth. So that's what I mean. That's closer to an analysis argument than a topological argument. But the point is, you can just assume in the proof that the path happens to be smooth. And once you assume that the path is smooth, then you can show that the image of F, or I should say G, on the sphere is of what you call measure 0, which is, again, that's analysis, not topology. Basically, what it means is that when you trace out the image, it has 0 area, which is the way it's supposed to, because a sphere is something that's two-dimensional, it has area, whereas a closed loop, that's one-dimensional, it's not supposed to have area, so it has measure 0 on the sphere. And because it has measure 0 on the sphere, you would say that almost any point you pick at random will be outside of this loop, and so there's lots of points you can pick, and then the argument goes through just fine. But you can see that you have to introduce calculus in order to make this work. So again, we're not proving this, we're not proving why the image is of measure 0. That's really appropriate for an analysis course. Maybe you've actually seen things like that. It's sort of like the mean value theorem. You can kind of cut it up into small little pieces, and then you can use the mean value theorem to bound how big the images are, things like that. But that's would be one way you can prove it, by introducing calculus into the proof. But as you can see, you use smoothness to make the argument be a lot simpler. Continuity, it's sometimes a little bit too hard to work with continuity directly. And that is really the purpose of smooth manifolds, that you have a very special topological space called a manifold, and most manifolds can be made smooth in the way that we're going to soon define, and that will allow you to often take advantage of ideas from calculus and use them to do topological proofs that would otherwise be difficult to do purely from a topological point of view by only using continuity. Now, I do want to say that some of you might be thinking that the topic of smooth manifolds is really a course in what they call differential geometry. And this is often where you see it. That is true. If you take a graduate course in differential geometry, you probably learn about, well, you definitely learn about smooth manifolds. So you might get the wrong impression that our course is a course in differential geometry. That is not true. But we will not be interested in geometry whatsoever. So we are only doing topology. We are going to be doing topology by introducing calculus. That's what we're going to be doing. When you do differential geometry, you also use smooth manifolds, but there you're interested in the geometry. You're not interested in the topology. So in differential geometry, if you have, let's say, a small sphere and then you have a big sphere, you would say that these are considered to be different. They have different sizes, they have different curvatures and things like that. For us, they're all the same. So we're going to be interested in topology. And there's a very nice book. Now you can find this, of course. So this material is, of course, in the Bredin book, because he has everything in that book. But a nice book, very nice book, is by Bott and Tu, and it's called Differential Forms in algebraic topology. And the book has a very interesting theme. It is a book in topology. And they do topology by using differential forms. So they do topology of smooth manifolds, and the tool that they use, the calculus tool that you use, is called differential forms. So differential forms is how you do calculus on a manifold. We will define what that means. If you ever go on to study differential geometry, or maybe you have, differential forms also come up in differential geometry. But we're not doing any geometry. We're going to be doing topology. And to do calculus on a manifold, you will need this notion of a differential form. And the theme of the book, it's a very interesting theme. The theme of the book is, it's a book on topology, but it approaches it from this differential form point of view. And the authors argue that this allows you to prove many of the difficult theorems in a substantially easier way. So that's really, you can argue, the main theme of the book. It presents topology from a very, from a more unique point of view. And that's what we're going to be doing. So you should not think that from this point on, our course has transitioned into differential geometry. It has not. We're going to be doing topology, we're going to be doing differential forms, and then you will see how it's connected with the previous topics that we've talked about in topology. So what we need to do is, we need to define what a manifold is, and then we'll define what it means to be a smooth manifold. So to do that, let me just maybe give a disclaimer that our definitions might be a bit different from other sources. So what are the different sources? Well, you have the Braden book, of course. Then I mentioned Bott and Tu. Then I mentioned another book you can look at is John Lee. He has a book on smooth manifolds. There's actually a book by Tu. It's the same Tu, but he written a book specifically on manifolds also. So these are just some of the books that have stuff on manifolds on them. And when you look at those sources, you might see that their definition is going to be a little bit different from what we're doing, but that's okay. I'm specifically doing the definitions the way we're doing it because I believe that this is the easiest way to do it. We're not trying to be as general as possible. We're trying to do things in a way that is friendlier when you first learn it for your time being. One can maybe sometimes argue that our definitions are not optimized, that they could be made better, and that is true. But for what we're going to be doing, it's going to be good enough. So let's begin by defining what a manifold is. Start with this definition. Let X be a space. So we say that X is an n-dimensional manifold maybe we can assume that n is at least 1. A zero-dimensional manifold would be a set of points. So let's just say n is at least 1. Some people talk about zero-dimensional manifolds, but let's not try to get too carried away with it. X is an n-dimensional manifold if and only if. So I'm going to write down the important part of the definition. This is the important part. And then there's a continuation of the definition, which is like the non-pathological part of the definition. But this is the one that you really care about. It basically says this: if and only if, for any point P in X, there is an open set in X containing the point so that U is homeomorphic with Rn. Okay, so basically, at each point, at each P on your space, X looks locally like Rn. So the common example is our favorite space, the torus, because if you pick a point on the torus and you look at a little neighborhood around that torus, well, it's like a disk, but that can of course be expanded into R2. So locally, it looks like R2. So that's the definition of what it means to be an n-dimensional manifold. But there's actually two other conditions here that I do not want to go into, and this is required to avoid pathologies. And furthermore, X is Hausdorff. You might find this a little bit surprising because locally it looks like Rn, and Rn is Hausdorff. So you might say, well, why does it not mean that globally that the whole thing is Hausdorff? Well, that's the strange thing. When we talked about topological graphs, I mentioned that some people require a topological graph to also be Hausdorff, and I gave you a fairly bizarre example of how locally it could be Hausdorff, but not globally. But that's what it means. Pathological, it's some hideous point set topology that we do not care about. And even more hideous point set topology is X is also second countable. If you have no idea what that means, it's not going to matter. Okay? Just, you can forget about it. The way this comes up is there are some technical proofs involving manifolds that assert that that they have certain properties, and you often have to reference both of these. That's why it gets included in the definition. Second countable means that it basically means that you can do constructions as a sequence. So a lot of the times in mathematics that the way we show that something exists is we construct a sequence of objects, and then sort of the limiting object is the one that we want. And sometimes if the space is too big cardinality-wise, you might not be able to arrange things in some kind of sequence for that to work out. You do not have to really worry about that. I mean, as long as you get this one, then that should be good enough for what we're doing. Some comments on the definition. If a topological space is an n-dimensional manifold, it cannot be an M. So you have the letter N and you have the letter M. So it cannot be an M-dimensional manifold because we know that Rn and Rm are not homeomorphic. We proved that before. So because they're not homeomorphic, if they have different dimensions, the dimension of the manifold is going to be well defined. There are some books that might also assume that your topological space is also connected, or maybe path connected. We're not going to do that. It's not really going to matter that much, but that's just what I mean. Depending on the source, they might vary the definition a little bit, but all of them will fundamentally have this one, that locally it looks like Rn. Another thing that I wanted to mention is sometimes we have spaces that are very close to being a manifold, but they're not quite a manifold. So for instance, the figure 8 space would not be a manifold because locally, no matter how small you try to make that, you see that X. And you can never make that X go away, no matter how small you make that neighborhood. If you do it around a different neighborhood, like if you do it around this one, then you see what you get. You get the real line, right? This is the real line, but if you do it around that one, you get two real lines intersecting at a point, which is not what you want. So you're kind of close to being to a manifold, but not quite. And maybe you can call something like that like a pseudo-manifold, but then the question, of course, becomes, how do you define something like that? How do you define what it means to be almost a manifold? That alone becomes its own set of complications. But we'll avoid that. What I would argue in cases like this, that if you're dealing with a manifold that's close to being, or like another example that people might use is, let's say you have like a cone. Let's say a cone. So if you have a cone, for the same reason as before, if you pick this point, you can see that looks like R2. But if you pick that one, it no longer looks like R2. Basically, it's like this piece, which can be flattened into the plane, and then you have the other portion on the other side that it can also be flattened into the plane, and then you have basically two copies of the plane joined at a single point. In cases like this, what you would probably do is you can then decompose the space into a union of two manifolds. So then you can kind of write it as, let's say, x1 and x2. You'll write x is the union of two manifolds. So then you'll have two manifolds meeting at a single point. So if it's what you would want to call a pseudo-manifold, then you'll just cut it up into pieces that are manifolds. That's probably what I would say typically what you would do, instead of trying to define what a pseudo-manifold is in general. That would probably be the better way to do it. And then you can be able to apply the machinery of manifolds to each of the pieces, and then maybe use some kind of like Meyer-Vitoris type of an argument or something like that to maybe get information about the entire space out of it. So this is the definition of what is a manifold. And maybe to emphasize, this is what we call a topological manifold. This is what we call a topological manifold. So in particular, this is what we have. So let's move this aside. So if X is a manifold, let's say an n-dimensional manifold, then we can find a collection of maps, possibly an infinite collection, but a collection of maps with the property that f lambda maps Rn into X, and f lambda maps, so these are mappings from the n-dimensional Euclidean space into X, into this more abstract topological space, and f lambda map the n-dimensional Euclidean space onto an open subset. Let's call it U lambda of X, so that X is then the union of all of these open sets. So why can you do that? Well, here's the reason why you can do that. It just has to go back to the definition of what it means to be a manifold. So if you give me a point, right, if you give me a point, there's this neighborhood, let's call it U, and that neighborhood is homeomorphic to Rn. Now, because you have a homeomorphism, you can, of course, take its inverse and go the other way. And so you have a map called F that's a homeomorphism with Rn and that open subset. And then you pick a different open subset. Then you pick a point that you have not chosen. Maybe you pick a point over here, and then there's a neighborhood. It is possible that maybe these two neighborhoods overlap, and they often will, but that's okay. And then you'll have another mapping from another copy of Rn, and then you have another homeomorphism here. And then you just keep on doing it throughout the whole thing, and you can create a collection of mappings. All of them map the n-dimensional Euclidean space into X, but they're not mapping it homeomorphically into X. Rather, they're mapping them homeomorphically onto an open subset of X. And all of those open sets cover all of X. So everything gets covered, which is basically this condition, right? That for any point, there is an open set. So for any point, the point will sit, any point in X will sit in one of these U lambdas. Now, if you look at this definition, so this definition is very similar to what we call a triangulation. But in fact, this definition is even simpler, because when we talk about triangulation of a space, we're not mapping. So in a triangulation, what we're doing is we're rather mapping the geometric simplex. And the geometric simplex, its dimension actually depends on the lambda. So the simplices, the geometric simplices, could come with different dimensions. And furthermore, there's also the requirement that the geometric simplices, their images, have to intersect in the common face. Whereas here, there is no such requirement. We're just saying all of these Rn's are mapped onto an open subset of X, and then all of those open sets have to completely cover X. Okay, so it's actually simpler than a triangulation, because you do not assume any other further properties other than the fact that their images are those open sets that cover X. In a triangulation, the images are actually closed subsets of X that cover your space, but it's very similar to that of a triangulation, but it's even simpler than that. And maybe what we can also add, that if X is compact, then we can assume that the indexing set lambda is finite, for a very simple reason, because X is a union of open subsets. If X is compact, then it means by definition you only need a finite number of those U's to do it, and so you only need a finite collection of such maps. Now these mappings, they have a name. These are called, sometimes these are called charts, or you can also call them coordinates. Charts or coordinates. You can also maybe call them coordinate charts. The idea here is very, very simple, because going back to our picture of the torus, so here's a torus, here is like a piece of the torus, and you're mapping R2 homeomorphically onto that piece. And by mapping it homeomorphically to the piece, you can introduce a coordinate system, right? The X and Y coordinate system, their images will give you like some kind of coordinate system right over here. It's going to be maybe some kind of curved or something, but you have like coordinates, right? You can describe where you're located on the torus, at least locally in that neighborhood. You can describe where you're located on the torus by using essentially the standard Cartesian coordinates. So that's why we call them coordinates. We also call them charts. This is a terminology from maps, from like world maps, like geography. When you have a world, so of course the world is a sphere, but let's say we lived on a torus, that was the world, then we would describe like a piece. If this was like, let's say, the United States, then we would have a local representation of that part of the world, and that would be a chart. If we went to over, let's say, Europe, then we'll have a different chart for that. And the collection of all of these charts, this is what we call an atlas, which is also a terminology from geography. An atlas is a book that consists of all charts. That's what an atlas is. An atlas, it has a chart for different regions around the world, and an atlas has to cover the entire world. So that's why the collection of all of them is called an atlas. So that's the terminology that is being used. Now, I want to give a little warning here, just a warning. Some authors define charts going the other way around. So they would say that you're mapping U, which is an open subset of X, into Rn. And they're often even more general than that. They might say that it's being mapped maybe to, let's say, a disk in Rn, or like a more general region. So it's going back to what I was saying earlier, that it just depends on whose author you're following. This is the way that I like to do it. I just feel maybe this is a little bit more intuitive. It is similar to something we've seen before with triangulation, so that's why I'm doing it. There's a cost and a benefit for always choosing to set up your definitions in a certain way. But this is the way we're going to be doing it. Okay, so this is the definition of an n-dimensional manifold. It has these charts. These are sometimes called, you can also call these local charts, because they're local coordinates. They describe what is happening locally in a manifold. And all of these charts taken together, you get what is known as an atlas. Okay, so this is the definition of a topological manifold. But we want to get to a smooth manifold, and that's going to be the next definition. Let us write down the definition again before we say what is a smooth manifold. Definition: X is a topological n-dimensional manifold if and only if it has an atlas. What is an atlas? That is, F lambda is a map from Rn into X, is a homeomorphism of Rn onto an open subset of X. Let's call it U subscript lambda. And that the union of all of those open sets, they glue together and they give you back the original space. I'm being a little bit incorrect here. I am skipping the pathological condition, and you also have to add if and only if it has this, and it's Hausdorff, and it is second countable. But let's not write that down, because this is the key idea. This right here is the key idea. So this is what it means to be. So if you say your space is a topological, well, usually we just drop the word topological. So when we say our space is an n-dimensional manifold, we just say this. Okay, that's what this means. Now this is the next definition. So let F lambda. So maybe we can just we call it script A to be the collection of all of these. B, an atlas for a manifold X. So we say that the atlas is a smooth atlas if and only if. So to define it, it's helpful to draw a picture. This blob represents X. This represents R2. Well, in general, Rn. This is being mapped homeomorphically. Let's call this F subscript lambda. This is some open set U subscript L. This is another copy of Rn. And this one is being mapped homeomorphically. Let's call this one F subscript mu, a different index. And this is going to be U subscript mu. And then they happen to intersect. Right? Now, they do not have to intersect. The two open sets do not have to intersect. If they do not intersect, then you have an empty condition and there's nothing to check. But if they do intersect, then they intersect at U lambda intersect U mu. That's how they intersect in X. To get the corresponding region in Rn, you just pull it back by F lambda, and then you pull it back by F mu. So you're going to get some kind of region over here, and you're going to get a region over here. It does not have to be a disk or anything. It could be rather complicated, but you have a region here and you have a region here. Now, this region that we have here, this would be F lambda inverse of U lambda intersect U mu. And this one down here would be F mu inverse of U lambda intersect U mu. And again, if these intersect in an empty set, these are just empty subsets of Rn. These have to be open, right? These are open subsets of Rn. The reason for this is actually very simple, because this is a continuous map. In fact, it's not just a continuous map, it is a homeomorphism. So these are open subsets. This is an open subset of Rn, and this is an open subset of Rn. So is a smooth atlas if and only if. Now, we want to consider the map going from this one to that one. So how do we do that? Well, you basically follow the arrows. If I want to go from here to here, I first go F lambda, and then I reverse back by F mu, which I could do because it's a homeomorphism. So we have if and only if. So we're going to do F lambda composed F mu inverse is smooth. And this is smooth in the ordinary sense, ordinary calculus sense. If you're confused by what that means, I'll remind you very quickly. But let's say you know what this means. I'm just going to write this. If you want to be more complicated, we do not want to be more complicated, but if you want to be more complicated, you would write F mu inverse composed F lambda, and this is a map from U F lambda inverse of U lambda intersect U mu into F mu inverse of U lambda intersect U mu. And this piece, this is an open set in Rn, and that piece, this is another open set in Rn. When you write it out like this looks absolutely horrendous. There's too many F's, there's too many inverses, there's too many things going on. But quite simply, what we mean is this composition has to be smooth. We have to understand that this composition is no longer, maybe this will make it easier for you. The space that we're working in, this is an abstract space. You cannot necessarily be able to visualize it in any kind of way. However, these charts that we have over here, this is the well-familiar Euclidean world that we're comfortable with. And we're basically mapping everything back to the Euclidean world where we are more comfortable in. And then when we talk about things being smooth, we talk about things being smooth in the ordinary Euclidean sense, which we're going to define right now. So what does it mean to be smooth? So in calculus, so this is in ordinary calculus, or maybe some of you like to say analysis. You see, there's this evolution that takes place for every mathematician. When you first learn calculus, you say calculus. Then after a few years, when you get more mathematically mature, you start saying real analysis. And then when you get more mature, you go back to saying calculus again. So then you're like, well, then what is real analysis? Well, real analysis, one would argue, is more about measure theory and stuff like that, right? People will tell you that's more what you do in real analysis. You're interested in being able to define measures and integrals arising from measures and things like that. And one would say that calculus, it's closer to what you do when you first go to university and they teach you calculus and differentiation, integration, fundamental theorem of calculus, all of that. And then when you get more mathematically mature, you then realize that manifolds is just a generalization of Euclidean calculus. So that's why you kind of go back to saying calculus again. So in ordinary calculus, say we have a function, for lack of a better name, let's call it f, and it maps from one open set to another open set. This is an open set, let's say this is an open set in Rn, and let's say this is an open set in Rm. Okay, they could come from different dimensions. In our case, it's the same dimension, but more generally, they could come from different dimensions. So we have a function from one open set to another open set. What does it mean for f to be smooth? Smooth basically means differentiable. So basically, f can be differentiated as many times as you want. Now this is a little bit harder to explain because if you're in Rn, you have lots of different derivatives. You usually call them partial derivatives. And then the other complication is the function, its target is an Rm. So it's a vector, an m-dimensional vector. It's not a scalar. So more precisely, we can write our function f as a bunch of scalar functions where each fi is a function from u into r. So these are called, you can call these the scalar components. And we require that each fi can be partial differentiated, because in multivariable calculus we talk about partial differentiation. In single variable calculus, we just, as you know, we just write f prime because there's just a single variable. But in multivariable calculus, we talk about partial differentiation. So we're saying that every one of these component functions that makes up the mapping can be partially differentiated as many times as we wish. So for instance, let's say we take the first component function, and then we take this first component function and we differentiate it with respect to the second coordinate, right? So, I mean, we would typically call that y, but of course, if n is equal to 50, there's no good letter choices in the alphabet. There's not enough letters in the alphabet to give a letter name. So we just call it the second coordinate, and then whatever we get, we can differentiate that to the first coordinate, and then whatever we get, we can differentiate that back to the second coordinate, and then differentiate it with respect to the fourth coordinate, and so on. We can do it as many times as we want. So we're saying that this derivative exists, and that gives you a function, and whatever function that is, it can be partially differentiated with respect to the first coordinate, and that will give you a function defined on u, and whatever function that is can then be partially differentiated with respect to the second coordinate, and so on. You can do it as many times as you want. The notation is a little bit unfortunate because it does look like the boundary operator that we talked about before, but we are mathematically mature enough to tell them apart. There's nothing to do with the boundary operator, but that's just the way the notation works out. And let me just maybe finish with a small observation. So that's what it means to be smooth in like the ordinary Euclidean sense when you're living in Euclidean spaces. Maybe you've wondered this. why do we use open sets when we talk about differentiate? So when we differentiate, why do we work on open sets? So when we work with derivatives, we our functions need to be defined on open sets. The reason for this is because let's say you have, just to use an example, let's say this is the domain of your function. So you have f, let's say fi, that's one of the component functions. Let's say u is this solid square, and you want to partially differentiate the function, let's say with respect to the x direction. So what would that mean? What would mean is you pick a point in the domain, and you have to calculate the rate of change that the function undergoes in that direction. Yeah. So at that point, well, the issue would occur is, what if you're located at the corner? Well, if you move there, then you escape out of the domain that you're located in, and that's the problem. That often when you calculate, like a lot of the times when you talk about differentiation of a function, you take a point and then you move in a certain direction, right? You pick some kind of direction in which you want to move. Usually it's one of the coordinate directions, but you can be more general. You move to like a different direction, and then you calculate the rate of change that occurs, and you shrink the vector down to 0, and you get some kind of limit out of that, assuming it exists. And that's what you call the partial differentiation with respect to that direction. And the issue, of course, happens is if this is not an open set, if you were to move in that direction, you escape outside the region. If you move in that direction, you escape outside the region. If you move in that direction, you escape outside the region. So there's like lots of different directions that you can move into where it would not make sense to talk about the rate of change. However, if this is an open square, you stay away from the boundary. And so no matter a point, no matter what point you pick, since we're interested in like making these infinitesimally small, we always stay, no matter how we move, we have the freedom to move around in the domain without the function escaping and leading to things being undefined. And so that's the reason why whenever we talk about differentiation of functions, we have to assume that we're working on open sets. Okay, so going back to our definition, that's what it means for an atlas to be smooth, that these coordinates or these charts, when you do these kinds of calculations with them, they will always give you a smooth function from one open set in Rn to another open set in Rn. That's the consequence of this. So that's the definition of a smooth atlas. So now let's say, what is a smooth manifold? Definition. We say, so a smooth manifold, so a smooth manifold is a topological space X together with a smooth atlas. So that is the definition of a smooth manifold. So if you want to be maybe a little bit more precise, so more precisely, you would often write X, comma, atlas. Okay, so it's a pair. It's a topological space together with a smooth atlas. Another complication, depending on the authors that you use, they make an assumption about an atlas that it has to be maximally large, whatever that means. But I do not think we'll need that. That will just give us complications. We're trying to avoid as many complications as possible, even if our definitions might not be the most optimal ones. I think for our purposes, that's going to be good enough. So that's going to be our definition of a smooth manifold. It's going to be a topological space, okay? And you want the topological space to be a manifold, so that means you have an atlas, okay? So you have an atlas, but you want the atlas to also be smooth itself, okay? So you need both pieces of data. So a smooth manifold is not a topological space. It's a topological space together with an atlas that has that smoothness property to it, okay? So this implies, of course, this definition implies, of course, that the same topological space can be different in the sense of a smooth manifold. So you can have the same exact space, but you might have a different smooth atlas. right? So you can have the same space, X, and you have a smooth atlas, and then maybe you have the exact same space, and then you have a different smooth atlas. And then you can maybe ask, like, they're going to be different, of course, but then maybe you can ask the question of equivalence. You can ask, maybe there's a way of making two different smooth atlases, treating them as being the same in some kind of sense. And we'll say something about that. That's actually one of the reasons why some authors, they require an atlas to be what they call maximal. It has to be maximal in a certain sense, because then that allows you to sort of, in some sense, eliminate the issue that you have two different atlases, but the smooth manifolds that you get are actually treated as exactly the same thing. But we're not going to worry about that whatsoever. Right? We're not going to worry about that in any way. That's not going to be an issue for us. So maybe I should say this is like the important point. So for us, maybe I should say this is the most important point, most important for us. We do not care at all how we get the smooth atlas. We only care that it exists. That is it. Okay? Because we will be interested in topology and nothing else. So we're going to be interested in X, right? We're going to be interested in the topological space. We're not interested in that atlas. So if we use a different atlas, and then you might ask, well, are these considered to be the same, or they're not considered to be the same? My answer would be, we do not care, because we're just focusing on the X. So then why is there an atlas? Well, the atlas is there to help you study X. If you have a different atlas, you still have the same X. Okay, so the topological space will remain the same. So we do not care how the smooth atlas arises. So whenever we say a manifold, whenever we say a topological space is a smooth manifold, it means it is possible to put on it a smooth atlas. You might put on it a different smooth atlas. Maybe you can put an infinite number of different smooth atlases, but fundamentally at the end, the only thing that you care is that you have a smooth atlas, and then you work with it. So now let's do some examples that illustrate this. Let us do an example involving a circle. Let us show that the circle, the one-dimensional circle, S1, is a smooth manifold. Now this is a little bit ambiguous because this is just a topological space. How can we say it's a smooth manifold? So what it means is, so when we say a topological space is a smooth manifold, what we mean is, we mean that S1 has a smooth atlas. That you can find a smooth atlas for it. You can maybe find a million different smooth atlases, but when we say that something is a smooth manifold, we just mean that you can put on it an atlas that has that smooth property. So here's how we do it. There's lots of ways to do it. So we're going to define a map. I'm going to call this map F+, and this is going to be a map from the open interval into S1. Now I am cheating a little bit because an atlas, we want to show this is a one-dimensional manifold. So an atlas has to consist of maps from R into S1. But R is homeomorphic to 0, 1. So if it bothers you, you can, of course, take a homeomorphism from R into 0, 1 and then compose with whatever that map is. But usually we just do not even bother to do that. So we're going to define a map from 0, 1 into S1 by the rule that F plus of t is going to be equal to e to the 2 pi I t. And the way you can visualize this, if this is the open interval and this is your circle, there is a hole over here because 0 and 1, they come together and they meet right there. And if your interval is, this is the orientation on the interval from 0 to 1, as you trace it around the circle, it will go like this. It will go counterclockwise, and it will miss that point, right? This is going to be like the missing point. So the image of that of this open set, of this open interval, the image of it does not cover the entire circle. To have an atlas, it means you have to have a collection of mappings so that the open sets you get on the circle, the union will give you S1. Okay, so this is a homeomorphism of this onto an open set. So let's call this open set, U plus, right? That's an open subset of S1. And then the other map, we're going to call it F minus. It's going to go from 0, 1 to S1, and we're going to be defined by F minus of t is going to be negative e to the 2 pi I t. So the picture for this one would be that if this is your open interval from 0 to 1, and this is your circle, then the way F minus maps this is by taking the interval, and it's going to wrap it so it's the negative of this one, so this would be the missing point on the other side. And then it will wrap the interval beginning at the missing point like this. It will still go counterclockwise. You might be confused. You might think it goes clockwise, but that's not true. Just carefully think it through. If you're going up like that, the negative of that is on the other side. You're just going like that. So it's still counterclockwise, but it just begins at a different point. So this is the way it wraps around the circle. And the image of this, we're going to call this U minus. And we claim that, well, maybe I should first say this. So clearly, the collection of these two maps, F plus and F minus, is an atlas for S1. It is an atlas because the image of F plus is U plus, the image of F minus is U minus, and these two open sets, they are being mapped homeomorphically to this one, which is homeomorphic to R. So they're homeomorphic to R, and the union of these two open sets, they exhaust and they give you the entire topological space S1. So you've satisfied the condition to have an atlas. But you then have to check. So now we check that it is a smooth atlas. Okay, so we have to check that F plus composed F plus inverse is smooth, F plus composed F minus inverse is smooth, F minus inverse composed F plus is smooth, and then F minus inverse composed F minus. I got these backwards. Yeah, I got these backwards. I meant to say this, that these are all smooth maps in the standard Euclidean calculus sense, that they're derivatives, that they can be differentiated as many times as you want. Now, this will just give you the identity map, which is differentiable. No need to check this one. This one will give you the identity map, and these two are very similar. So let's not even bother. Let's just do that one because the other one's going to be very similar to it. So we're just going to show that this one is a smooth map. So we have to figure out what F minus inverse from F plus is. So this is going to be something it's going to map an open set in 0, 1, and is going to map this to another open set in 0, 1. The reason why it's 0, 1 is because instead of using R, it was more convenient to just use the interval from 0 to 1. So that's what we're going to be working with. So there's going to be, so we're basically mapping, so the idea is this. You see, F plus goes from here to our space, and then F minus returns us back to the interval. So we're kind of going from here into the space, and then we're returning back to the interval. And so this composition will take us from this one to that one. And so we're now back in single variable calculus, and we're arguing that what we're getting is going to be smooth. So we have to calculate what this is. First, maybe we can find the domain for this. Maybe that would be helpful to find the domain. So to find the domain, you have to intersect these two. So if you do U plus intersect U minus, you'll have two missing points, right? And then you have everything else filled in. And then you're going to pull this set back, right? This is how these two open sets intersect. Then you're going to pull this back by using F plus, and you're going to pull this back using F minus. So when you pull this back using F plus, you're going to get, this is the point that goes to 0, and this is when you go halfway around, right? Halfway around. So you're going to have a missing, you're going to have 1/2 will be missing. And here, this is one of the missing points, and the other missing point occurs halfway around. So this will be the other missing point over here. And so this composition is going to go from this set to that set. So more specifically, this is going to map 0/2 union 1/2 1 to 0/2 union 1/2 1. So it's basically everything just minus that point at 1/2. So we have to figure out what this function is. So F inverse, I wrote -1. I just meant to say minus. So F minus inverse of ft, I'm sorry, of F plus evaluated at t, that would be equal to, and here you just have to carefully think this through. It's going to depend whether t is in this interval or whether t is in that interval. So if t is chosen in this interval, let's see what happens in our picture. So if you choose t, let's say over here, then the image of t, of that point, it kind of gets wrapped before halfway. So it'll be right over there. But then you have to figure out the location of t with respect to this interval, the other mapping. So this is the one that starts down here. This is halfway around, and it continues further on. So it's going to be in the same position, but shifted over. It'll be shifted over on the other side by 1/2. So that would be located at t plus 1/2. And so the way this function is going to be defined, that composition, this is going to be t plus 1/2 if t is between 0 and 1/2. And then you can think about what happens if t is between 1/2 and 1, but you can probably guess what that would be. That would be t minus 1/2, right? So if you're located in this interval, you get mapped over to this one, and if you're located in that one, you're going to shift back by subtracting away 1/2, and then you'll be ended up in this one. So this is what the composition is, and this is clearly a smooth mapping. Okay, if you're concerned about piecewise conditions, there's no problem whatsoever because these are open conditions. It's not like we're saying it's not like we're saying for t less than or equal to 1/2, right? We're not saying that. These are open intervals. So on this entire open interval, this is a smooth function. You can differentiate it once. In this case, there is no partial differentiation here because this is just a function of a single variable. But if you differentiate it once, you get 1/2, and if you differentiate a second time, 0, and then you just can differentiate it as many times as you want, and the same thing with the other one. So this is a smooth mapping. So we have shown that the atlas that we have just constructed is a smooth atlas. But, okay, so we have shown that S1 is a smooth atlas. I'm sorry, is a smooth manifold. But there's other ways to do it, right? So when you say something is a smooth manifold, you're only saying that there is a smooth atlas on it. There could be lots. I'm going to show you another one. I'm not going to work through the details. That would be a homework problem. But just to go through it. So another smooth atlas on S1. And this is basically stereographic projection. I know we usually talk about stereographic projection of the two-dimensional sphere, but this is the same idea. You're going to define a map. Let's call it Fn. N stands for the North Pole. And this one's actually going to go all the way from R into S1. And I'll just draw you a picture. So this is S1, okay? And then you have your real line going through the center of the circle. And you have your North Pole, that's the N. And you have to map a real number onto a circle. And the way you do it is, if you have a number x on the real line, you just draw the line to the North Pole, and where it intersects, you call that Fn of x by using the North Pole. And you can do the same thing by using the South Pole. And then you can show that these two mappings taken together is a smooth atlas for S1. So in fact, it is a different smooth atlas. The fact that it's different from the other one really does not matter to us whatsoever. We just care that it exists. Though an interesting question you can ask is, so we have two atlases. This is the one that we did before, and this is the new one that you'll check on the homework. Let's call it A prime. Is there some notion of like equivalence? That, okay, maybe they're different, but maybe in some sense that they're equivalent. So as I've said before, there are some books that would not allow this. This will not be in the definition of what it means to be an atlas. They will require this to be maximally large. And then it will follow that the previous one that we looked at and the new one that we're looking at, they're part of the same maximally large family. So in the end, you actually get not just equivalence, but you get the exact same thing. But we're really not going to care about that. And I do want to get to this notion of equivalence. We could still define what it means for two smooth manifolds to be equivalent in some kind of sense. So I do want to at least get to that. Now we will define what it means to be smooth, a smooth map in a manifold sense. I'm going to define smooth map between x and y, where x and y, these are where x and y are smooth manifolds. Now, we are being very, very sloppy, as we normally are in mathematics. When we write x and we think of x as a smooth manifold, we really mean x with some atlas. So let's call this atlas F lambda. And y is, it has its own atlas. Let's call it G mu. Okay, maybe call this a different name. Maybe we'll call this phi. So x and y are smooth manifolds. Smooth manifold means it's a topological space together with an atlas, which is smooth. So you need to make that choice. Without making the choice of an atlas, you will not be able to define what it means to be a smooth map between two manifolds. And then here's the way we define what it means to be smooth. Well, we know what it means to be smooth in the ordinary calculus sense when you map everything back to Euclidean space. But it could happen, let's say, that maybe x is an n-dimensional manifold and y is an m-dimensional manifold. And so the reasonable way to do this is you're mapping, this is phi, and then you have Rn, and you pick one of these charts, right? You have one of these charts, F lambda, and then you have Rm. You have one of these charts. We call this G mu. And you're going to reverse it the other way around. Now, you do have to be a little bit careful over here. When I'm going to write over here G mu inverse, I'm not actually saying that you have a map from all of y. Rather, it's the open subset of y on which this one is being mapped into. And then you have a map between these two, which is this composition. So it's going to be F lambda composed phi composed G mu inverse. If you want to be a little bit more careful, you would say that F lambda maps this not, it's a subset of x. It's really being mapped to U lambda, which is a subset of x. And then phi, and maybe we get rid of phi for now, and this one, this G mu, is mapping it to an open subset of y, which we'll call v subscript mu, and that's an open subset of y. And x and y are smooth manifolds, and we have a map between them, which we call phi. So we can, of course, restrict phi we can restrict phi to this one, but it does not necessarily map it into this one. It does map it into y, but the image of it is not necessarily this one. So when we do the composition, we go into this one, then you have the image, phi, you have the image of this. So it is conceivable, of course, I should say, that this could be the empty function. So for instance, this gets mapped to an open set, and that open set gets mapped into something that does not intersect with this one. Right? The only thing we know about phi is it's sending this open set to some set, and not even necessarily open, in y, and it might not even overlap with that one. In which case, this composition will just be the empty functions because the domains and codomains do not properly line up. So that's all what that would mean. And then there's nothing to check. But in general, that's what it would mean to be smooth, that this mapping, this would be a smooth mapping in the ordinary Euclidean sense. So that's what it means to be a smooth map between two manifolds. And let me give you an example of this. So let's take this away. Let's look at this example. Let R, comma, identity denote the R with the identity chart. Now this might be a little bit confusing because we have two different R's. This R, we're thinking of this as a smooth manifold. And this R, we're thinking of it as the Euclidean space. So the idea is that in order to describe a smooth manifold, we need a Euclidean space to represent it as a chart. And that's what we're doing. So we have two different R's over here, but they're kind of serving two different purposes. This is sort of like our topological space, and that's the chart that we're using to give it a smooth structure. And we're going to let R, comma, I'll write it like this, with a cube, denote R with the cubing chart. So this is the map that takes us from the Euclidean space R to our topological space R, but it cubes everything. So that would just mean that x gets sent to x cubed. This is going to be a homeomorphism. This is a one-to-one mapping. If we use a square, we would have a problem because it's not a one-to-one mapping. But this gives us R with a different smooth manifold. Okay, so with a different smooth atlas. So we have two versions of R. So maybe we'll call this one. Maybe we'll just call this. We'll just call this maybe. Let's maybe call this R1 because this is sort of like the identity map. And maybe we'll call this one R3 because this is the cubing map. So as a topological space, okay, so R1 and R3 as topological spaces are the same. It's just the real line. But they have different, you call it smooth structures. Here, we only need a single chart. On the circle, we need a minimum of two charts in an atlas. But for the real line, you can get an atlas with just using a single chart. Okay, so this is what we have. And I want to show you something kind of interesting that so then the map from R1 to R3, and let's say this is the cube root map, is smooth. Why is it smooth? Well, to check that it's smooth, you go back to the definition. You pick something in the chart. You pick something in the atlas. There's only one thing in the atlas. It's just R. This is the identity map. You pick something else in the atlas for this one. This is just R. This is the cubing map. And then if you follow this through, so if we kind of think this through, this is X. X gets sent to X. X gets sent to X cubed. And then the inverse, well, the element in R that gets sent, I'm sorry, this is the cube root of X. So I guess that is not going to work. Maybe I should have done it. Maybe I should have done it a little bit differently. So let me do it like this. Let's say this is R3, and this is R1. So X gets sent to X cubed. Then the cube root map from R3 to R1 will then send it back to X. This was the cubing map. And then this map is the identity map. And so this X then returns back to X. So you can see that on the level of charts, the map, the Euclidean map, is just the identity map on the level of charts, okay? On the level of charts. And this up here, this is on the level of manifolds, of smooth manifolds. So if you want to check that something is smooth, you send it back to the charts and you check that it's smooth on the chart. So on the charts, this is just X going to X. This is a smooth map. The identity function is infinitely differentiable. So we have shown that this mapping is smooth. However, if you go from R1 to R1 by using the cube root map, is not smooth. Well, why not? Well, because when you send it back to the charts, this is the identity, this is the identity, and then the level of the charts, this is just back to the cube root map. So X is being sent to the cube root of X. But we know that the cube root function, in the ordinary calculus sense, it's not differentiable at the origin because you have that vertical tangent, infinite slope, undefined slope, or something like that. So this is not, so this one is, you can see, not smooth. So it's an interesting example. It just shows that, so this example shows that being smooth depends on what atlas you use, even if the topological spaces are the same. And like I said before, this might bother you because you might look at this word smooth and then say smoothness. So this is what you can say. You can say that smoothness is not a topological invariant because being smooth depends on the atlas. It does not depend on the topology. And you're absolutely correct. It is not a topological invariant, but that's okay, right? As we've said before, when we deal with smooth manifolds, the only thing we will care about is it has a smooth atlas. So once we pick that atlas, we do not really care if there's a different atlas where the notion of what it means to be smooth or not will change. That's not going to matter to us. And let's also say, what is a diffeomorphism? So definition, let X and Y be smooth manifolds. So again, we're assuming that we have an atlas here, a smooth atlas here. We often do not even reference it unless we have to be smooth manifolds. We say that a function from x to y is a diffeomorphism if and only if f from x to y is a smooth bijection and its inverse is a smooth bijection. Well, there's no need to say bijection again because it's definitely going to be a bijection, but the inverse map is also smooth. It's just like when we say a homeomorphism, but now we're just replacing homeomorphism by the word smooth. And going back to our example, so R1 and R3 are different smooth manifolds. So just to say this again, this is the real line with the identity chart with an atlas consisting of a single chart, which is the identity chart. And this is the real line again, and its atlas consists of just a single chart, and that's the cubing function. So these are different smooth manifolds. We saw that when you go from R1 to R3, like when we map one of them into the other by the cube root function, in one of them it's smooth and the other one it's not smooth. So these are different as far as smooth manifolds are concerned. They're considered to be different smooth manifolds. However, R1 and R3 are diffeomorphic. So yes, they're different, but in some sense they're equivalent. And what's the diffeomorphism? Well, you define the following map from R1 to R3, and the map is you take x and you send it to the cube root of x. That's the way you do it. Let me just check again that this is correct. I messed it up. I think I have to go from R3 to R1 like this. So that's the function. Yeah, so this would be the way to do it. And then the reverse map, you can check. It's not difficult. From R1 to R3, this is going to be the one that sends x to x cubed. That's the inverse one. You can check that that one will indeed be also smooth. So that means that even though you do have two different smooth manifolds, in some sense, you can say that they are the same. Using the other example that we saw was we had the circle and we had an atlas and we had these two maps. One of them wrapped the unit interval around the circle with a positive sign, and the other one wrapped the unit interval around the circle with a negative sign. And we saw that this was a smooth atlas. And then you can do it the other way. You can use stereographic projection from the North Pole and stereographic projection from the South Pole. So the unit circle, this is one type of atlas, this is another type of smooth atlas, and it's not very difficult to check. You can come up with a diffeomorphism. So these are going to be diffeomorphic to each other in the end. So here is, I'm going to mention some interesting theorems that we will not need, but I just want to mention them because they're interesting. Here are some interesting questions / theorems that we will not need because we're doing topology. So we will not care about this. But this is from a field of topology called differential topology. Okay, so here's the questions you can ask. So here's like question 1. Suppose X is a topological manifold. Can X always be smoothed? In other words, is there a smooth atlas on X? Right? Topological manifold just means there is an atlas using continuity, but smooth atlas means you want those functions on the, when you bring them back to the Euclidean space, that they're smooth functions. Another question you can ask is, given a topological manifold, are all smooth structures, and by smooth structures we just mean smooth atlases. That's just another way to say it. When you put a smooth atlas on your manifold, you call that a smooth structure. Are all smooth structures diffeomorphic? Because we just saw the example where the real line can be given two different smooth structures, but in the end they're diffeomorphic. Or the circle, where you can put two different smooth structures, but they're going to be diffeomorphic in the end. So are all of them diffeomorphic in the end? And these are very difficult questions, right? These are very hard questions. And I'll give you the answer to this because this is well known now, but for a while, mathematicians were very confused by this. So what I want to say about, so let's talk about question 1. So let's write this theorem down. If X is a smooth manifold, then X can be smoothly triangulated. Whatever that means, but it could be triangulated. So a smooth manifold can be triangulated. So we know what that means. Smooth manifolds have a triangulation. And there are examples of manifolds, topological manifolds, which cannot be triangulated. Therefore, they cannot have a smooth atlas. Actually, maybe for those of you who might be interested, all of you know who Moncrief is. And Moncrief, who is still alive, I think he's 90 years old, Moncrief does research in differential topology. So if you ever wondered what is it that Moncrief does, so he works in differential topology. In differential topology, you're not interested in the topology anymore. You're interested in the smooth structures you put on the manifold. That's why we call it differential topology. So if X is a smooth manifold, then X can be triangulated. This is a theorem. This is a very difficult theorem. It goes to Whitehead. Now, there are examples of manifolds which cannot be triangulated. These examples are very hard to give. In fact, I've never even seen an example myself. I just know that they exist. But it's like a well-known thing. People who work on this, they will tell you they know it's not that. I've never actually seen the example myself because supposedly they're very hard to actually explain. So yes, you can have topological spaces that do not have a smooth atlas. Here is another theorem that if X can be triangulated, then X has a smooth atlas. And maybe to say this, that every two-dimensional, every n-dimensional manifold where n is less than or equal to 3 can be triangulated. So in particular, so you can, when n is equal to 2, you often call that a surface. So a surface can be triangulated, and therefore you can give it a smooth atlas. When n is equal to 3 was proven in 1970s by Moyes. And Moyes happened to, he's not alive anymore, but he happened to have been the PhD advisor to Moncrief. So Moyes proved that three-dimensional manifolds can be triangulated. So in particular, that means there is a smooth atlas. And if you're doing topology, you only care that a smooth atlas exists. So that was proven by Moyes. However, it is known that for n is equal to 4 and onwards, and so on, and it's always n is equal to 4 if you ever noticed that. Like in mathematics, when things break down, it's always at dimension 4. Very interesting how that happens. So it is known that for n is equal to 4, manifolds in general cannot be triangulated. However, those are pathological, and the ones, and maybe we can say the explicit ones, the explicit manifolds that we care about, are all smooth. Right? They can be triangulated, so they can be smooth. So it's just that in the universe of topological spaces, you cannot just assume that it can be made smooth. But the kind of manifolds that we come across in practice and we want to analyze, those happen to be smooth. So we have this. Now, the other question, actually, maybe I should say this. So when Perelman proved the Poincare conjecture, he was working with a three-dimensional manifold. So he could assume that it was smooth, which he had to. So the proof of the Poincare conjecture, not that I know what it is, I've not learned the proof of the Poincare conjecture, but I just know that when we talked about it in class, we said that it uses something called geometric analysis, where you're trying to analyze the behavior of a PDE on a manifold. But in order to talk about the behavior of a PDE on a manifold, you need it to be smooth. Otherwise, it would not make sense about what you even mean by a PDE. So this was what Perelman did from the very beginning. It is known that three-dimensional manifolds can be triangulated. Once they can be triangulated, then there's a separate theorem that says that you could make them smooth. So Perelman, from the very beginning, could have just assumed that he has a smooth manifold and then work from there. So as you can see, that even though the Poincare conjecture, it's a problem, it's just a purely topological problem, in order to prove it, he had to use smoothness to help him say the things that he wanted to say. Now, this is sort of addressing question number one. What about question number two? Talk about question number two. So here's something very strange. So it is known that r to the n that all smooth structures are diffeomorphic. So we did the example with the real line, and we gave two different smooth structures, but they were diffeomorphic to themselves. And the exception is when n is equal to 4. It is known that there are infinitely many, you can call them fake R4 smooth structures. You sometimes call them, you can sometimes call these exotic spaces. You can call it like an exotic R4. Now, the obvious way to do it, right, the obvious smooth structure that you put on R4 is you take R4 and then you use the identity map. So you use an atlas consisting of a single chart. That's the most obvious way to do it. But there's other ways to do it which are not diffeomorphic. So it's just interesting that all of these Rn's are diffeomorphic to each other, no matter what kind of smooth structure you use, but then everything falls apart for n is equal to 4. And also, you can ask, well, what about Sn, the n-sphere, another commonly used topological space. So this was studied by John Milner, who's also still alive. He's 90 or 91. He's at Stony Brook, by John Milner, and those are called exotic spheres. So John Milner realized that for some dimensions, and I do not know anything about differential topology. This is not an area of math that I studied, but I believe there's a finite, I might be wrong on this, so you have to look this up. So there are a finite list of exceptions for n, for which we have what is known as exotic structures on the sphere. And those have been all found. And the number of smooth structures has also been determined. So I think, and again, I did not look this up, but I think there might be an exception for S5 or maybe S7, that there's more than one different smooth structure you can put on it. So that would just mean a different smooth atlas, which is not diffeomorphic to the usual way of doing it. Let's say stereographic projection is probably the easiest way to do it, because you just have an atlas consisting of two charts. But yes, there's other ways to do it, and you can even I think there's a known result about which dimensions are exotic, and also the full description of how many you have. So that's something that is understood. And if you're interested, this area of mathematics is called differential topology, because you're more interested in the smooth structures on the space than the topology itself. And I do not know anything about it, so I cannot really help you further with it. But if you're interested, this is something you can look into. And as we've said, even though these questions are interesting and they're very difficult, we're not going to be concerned about any of these questions, because, as we've said, no matter what smooth structure you put, the space will always remain the same. And we're going to be exclusively interested in the topological space only.